So I'll do the introduction. Thank everyone for coming to the final day of PETSc 2025. I hope you like the dinner. So we'll have 2 sessions of talks today, and then at the end, we're going to have a discussion. We're going to lead off the discussion with where should the next meeting be. So if you have ideas about that, show up to that, and we'll try to do it expeditiously. I know people have flights. And then some of the larger discussion topics we always like to ask is, what do you think is wrong? What do you think is missing? Things like that. Or what do you think is an opportunity? Or how do you do this particular complicated thing? What are our ideas for doing that in a nice way? I think those are fun kind of topics. It didn't occur to me to really ask Blaze if he would like to give a talk in the morning. So administrative snafu. So I will just talk a little bit about stuff, and then we will have Zoe give a real talk. And so I want to talk about a theory of mesh transformations that I've been working on for a while. I've given a few talks. So I was thinking that sometimes it gets too technical, and it shouldn't really be that technical. You can almost do all of this in pictures. So I'm going to try to do all of this in pictures, no words. I have worked on some of this with Toby and also Dan Shapiro. And the way I got the idea to do this is Grant Sanderson, who is really dedicated to trying to make stuff simpler and more accessible. And I applaud that. He's my favorite math presenter, I have to say, when I watch a ton of his videos. So the job we want to do, the simplest way of seeing is, suppose I give you New York State and you'd like to do something like solve some surface evolution problem. You need a way to break up New York State into pieces so you can approximate the elevation and the change in elevation across the state. So here's a way you can do that. And what I just did, you can do from the command line in PETSc. I can read in the SHP, the shape file, which is a GIS format, and then I can use triangle to triangulate this, and then I can do different things to it. So I want to briefly say how we think about meshes. So I think in this room, it might be pretty natural to think about dividing up space into little pieces where the pieces share boundaries. So, I have piece 0 here, and it shares boundary edge 21 with piece 1. And so you could say that I divide up this into maybe polytopes or more complicated shapes, and their closures are the things that intersect. And this kind of structure is what a CW complex is intended to capture. And so we can kind of split them apart with replication. And this is how most mesh generators and programs think about meshes. It's not the only way you could possibly think about meshes. You can do the dual. You could say, oh, well, the things that are really independent are these vertices here. And vertices have stuff attached to them like edges and cells. And these cells are replicated, and I store kind of these star-like things. And so I can do this, but the default setting in PETSc is to treat things like this rather than that. Although if you look at this, this is much more like what finite volume things want to see. So let me just quickly tell you what I see when I look at a triangle like this. So I would say, well, there's a cell, 0, but it doesn't contain its boundary. So the cell is attached to a boundary made up of 3 edges, 4, 5, and 6. And then these edges are actually the interior, and they have boundaries which are these vertices, and these vertices are replicated. And so this is how combinatorial topology works, where you often do formal sums, and you could say, okay, so 0 is kind of, the boundary of 0 is kind of the sum of 4, 5, and 6, and then if I take the boundary of that, and I sum them, but I sum them with orientation, then these will all cancel out, and I will get the boundary of a thing vanishes. And these are the kind of formal manipulations that they do. So you can represent this kind of structure as a directed graph, because you're directing from things to their or from the boundary of things to their thing, some kind of adjacency relation, and then I can add on the boundary of these edges to be vertices. This graph is acyclic because you never get an edge pointing back from a higher dimension to a lower dimension, and so it's a DAG. And this DAG has a name, it's the Haas diagram, and you can do more complicated things. So here I have two cells at the bottom covered by 5 edges, and you can see that A8 is shared, covered by 4 vertices. And this is enough to do an awful lot. So for instance, if I want the closure, the topological closure of 0 is actually the transitive closure in this graph. And there's an isomorphism between every CW complex and a DAG. It's Haas diagram. And you can take the dual of that. So if I want to know what might be the support of a function associated with 0.5, I can take the dual of the transitive closure and get that function would be supported on these 2 edges in this face, but not on the far face. And so to get more low level, how are these things represented in memory? Well, the things attached to 0 are 6, 7, 8. The things attached to 1 are 9, 10, 8. And then the things attached to 6, 7, 8, 9, 10. So if I wanted to do something like get the closure, and so look, this is why tech is amazing, because instead of writing little CL, I can do things like that I think make much more sense for transitive closure. And it would be 6, 7, 8, 4, 2, 2, 3, 3, 4. And that's exactly what I expect to get. And then I could eliminate duplicates if I want, which I usually do. Yeah.
This might be too low level of a question for this talk.
Yeah.
So I appreciate if we have to talk about this offline. But like, you actually, when you're talking about the binary representation of these things, store like orientation information for, I guess, 0 and 1.
I'm going to do it. Right now. So if you have 1, if you just stack things up, 9, 10, 8, 3, 3, 3, 5, 5, 4, 3, 4, it's backwards, right? I want that edge, and so this is not enough. So here it's in the right order, but here it needs to be reversed. So how do you think about that? And how I think about it is that orientations are decorations for the DAG edges in the Haas diagram. And what do those integers mean? Each integer is labeling an element of the dihedral group for the k-1 face that's being attached to the k face. So basically, how do I twist it or flip it around before I attach it? And this is an old concept. This is from the 1920s. This is how combinatorial topology was formulated. How do you attach a k-1 face to a k face?
So, what's the setup? So here, for instance, you look at the 8th edge, and it's flipped in the cell number 1.
Uh-huh.
But what defines the fact that the 8th edge is 3 to 4 and not 4 to 3? You don't see it on the graph.
Oh, yeah, you don't. And that's why I was pointing it out. So there's a canonical order in memory. And so the order is this transformation is with respect to the canonical storage order.
So a priori, you decided arbitrarily.
Arbitrarily.
3 to 4 or 4 to 3.
That's right. There's no way that I know of a priori to decide an order. Yeah.
How do you, like, when you say it's arbitrary, at least in DL2, just like the first time when you assemble the mesh, you see a face, that is the orientation of that face.
That's right. That's how I do it. The first time you see it, I take that order. Yeah. But I have things like orient, where you can take an unoriented mesh and orient it if possible. So if you feed it Mobius, it'll return this is not orientable. But if it's orientable, it will give you an in one of the possible orientations. Yeah. So this won't work. So now that's how you represent things, but I'm much more interested in how you transform things from one representation to another. So suppose I wanted to do something like this, regular refinement. So I'm introducing, in place of one triangle, I have 4 triangles. I take every edge and I break it in half. I introduce 3 new edges and 3 new vertices. So how do I think about doing this? Well, these vertices are invariant. So in fact, the old vertices just reproduce themselves. The edges, each edge gets broken, and in the process of breaking it, I introduce a new vertex. So let's look at how that works. So I have this bottom edge, and I want to produce this left section, 13. And so how do you know what 13 is? 13 is fully defined by its cone, by the boundary. So if I tell you I have an edge 13 and here's the boundary, then you know exactly what 13 is. So the left boundary point comes from 1. It just reproduced itself. The right boundary point comes from breaking 4. So if you imagine that there's a tabular description of what's happening, vertices, nothing happens. So I just reproduce myself. For edges, I produce 2 sub-edges, and those things have cones that I have to describe. And so how would you describe them? So first, I would say, well, the left part of the cone, the left part of the boundary of 13 is coming from 1, and so I would say, okay, 4 is producing 13. I want to identify that point. So I take 1 cone of 4, and I get 1. So the cone of 4 is 1 and 2, so I take the first one. So 1 cone, 0th member of that cone is 1, and then the 0th thing produced by 1 is 4. Yes?
Define cone.
Yeah.
Define cone in this context. What do you mean by cone in this context?
Oh, cone. Cone's the boundary. Sorry. I will try to say boundary. Cone is jargon. I will force myself to say boundary. If I want to describe 7, I can say, well, 7 is I take 0 boundaries of 4, so I get 4, and it's the first vertex produced by 4 is 7. And I can describe 14 the same way. 7 is described the same way, 0, 0, and 5, you take 1 boundary of 4, which gives me 1 and 2. You take the second point, which is 2, and you take the first thing produced by 2, which is 5. So if you imagine, there's a tree of production, you sort of go up in the original mesh as many times as you need to go up, and then you go down and you pick the produced thing you want, and you produce a given number of types, and you dispatch by what kind of thing you're producing. Yeah.
So is it significant that vertex 1 is now vertex 4? Why not just call it vertex 1 again?
Let's see. It's because those 1 and 4s are not significant by themselves. It's just that I'm numbering the whole mesh, and there
was one cell that was 0. Now there's going to be 3 cells.
0, 1, 2, 3.
4 cells.
4
0,
cells.
1, 2, 3. And
Yeah.
so vertice counting is going to start at 4.
Yeah.
That's all really.
Okay, so you globally enumerate all geometric things with one contiguous indexing.
That's right.
Okay.
Locally, though.
But starting with cells first. Always.
That's right. Always cells, vertices, faces, edges, so I can throw away faces, edges, or put them in without altering the numbering.
But the fact that you number cell first
Yeah, you have to
has
know.
absolutely no bearing in this context.
In this context, no. Well, you could do whatever numbering you want. I do it for efficient indexing. So if I want to talk about how to produce these cells, I would say, okay, take the first subcell. It has a boundary of 13, 12, 18. So I need to describe the boundary of each one of those things. So if I take one boundary of 0, I get 4, 5, 6. If I take the first entry, that's 4. And if I take the first edge produced by 4, that's 13. So 1, 0, 0 is enough to tell me 13. And then I can do the end one the same way. You take one boundary, which gives me 4, 5, 6. You take the third member, which is 6, and you take the second thing that it produces, which is 18. But I got to do the middle one. The middle ones actually doesn't come from breaking an edge. It comes from being inserted for a face. So I take no boundaries of 0, so just 0, and then I take actually I number up the produced things as first, second, third. So I take the third edge that gets inserted in 0, and that's 12. But I have to reverse it. So I hid from you the fact that all of these descriptions also need an orientation at the end. Yeah. So you need to say how many cones or how many boundaries do you want to take, the member of each boundary, and then the replicant that's produced by that point, and then the transformation I need to do to that thing in its orientation in the original to get to the new. So it's not with respect to canonical, it's with respect to how it's oriented in the original thing. So if 12 was backwards in the original thing, then it has orientation canonical in the new thing. Yeah. So that's why all of these are not describing invariant things. They're describing a group element, transformed from what you have to this. And so this is the complete table for regular refinement for triangles. And this is how it is typed into the code. And I wrote one function which runs over a table and then uses that table to transform the input mesh to an output mesh. And all you do for different things is change the table. So it's a pretty small piece of code. So here's doing it in 3D. So in 3D, one tet is broken into 8 tets. So let's think about the corner tet. And let's think about the bottom face of the corner tet that gets produced. This introduces another wrinkle associated with orientation, because if we go back, this face is one of the 4 faces that are produced when I split the bottom face. So if you go back to the triangle table will say, oh, well, this I know how to make this. But that bottom face could have been attached with some orientation. And therefore, I need to know which of the possible orientations it's attached with, because for the canonical orientation, I get red face. But it's a different face for all the other orientations. In fact, it's a different face and it's oriented a different way. So you need a table. If originally I had orientation 0, I have the 0th face and that is orientation 0. But if originally I had orientation 1, then I take the first face and it has orientation 1. And you can write these down. So you need a table of the transformation of orientations from the parent to the child. And I thought I could derive this and failed several times. And so I just wrote them all down. And so Dan Shapiro tells me that he can derive these, or maybe Toby will derive them. But I could not do it yet. So you could do other things. So for instance, here's using this tabular thing to change all of the triangles to quadrilaterals. So how does that work in a tetrahedron? Well, I could break the tetrahedron into 8 hexahedra. And so what happens? So you break all of the edges in half, just like we do for regular refinement. You break the triangles, but you break them into 3 quads instead of 4 triangles. And then you, what you end up doing is inserting a vertex in the middle of the tetrahedra and edges that connect it to each face. And then if I consider something like this hexahedra, so there's 4, let's see, there are 4? Yeah, 4 hexahedra that get produced. So I can do it to my original New York State the same way. You can also do this for extrusion. So this is an extruded thing for groundwater flow.
Does your extrusion have sort of the same tabular format?
Yeah. So I'm going to do it. So how does it work? So you would think, oh, I'm changing dimensions. How do I change dimensions? Well, you say, all right, one vertex ends up producing multiple vertices. And it also ends up producing the edges between those vertices. You're allowed to produce multiple types in the table. Then each edge ends up producing multiple edges and also the faces that go between these edges. Why doesn't it produce the edges on the sides? Because those have already been produced by the vertices. So what happens? When you want to describe the boundary of this guy, well, you know how to describe these two because you just produced them. And how do you describe these 2 edges? Well, you say, I'll take this edge, take one boundary, which is 11 and 15, take the first element of that, which is 11, and take the first edge produced by 11. So it's the same tabular format, and I just write down that boundary. And then, it's easy to compute. It's the first edge or the second edge or the third edge produced by 11. And then a bunch of faces are produced by the original cell and the cells that go between them. And I can describe each one of those boundaries by taking a number of boundaries in the original mesh, then taking some point in that boundary and taking the cell, some replica of the produced points from them. You can do things like this, which is a triply periodic Schwartz P surface, which we extruded symmetrically about the surface. And I think that's all we did. So the last thing I want to talk about is I would like to get to the point where, as I said, I have typed all this in by hand, but it would be nice if we could write down a theory for it and have all those tables generated and prove that they are correct, which is...
I know what that theory is.
Oh, yes! Okay, so Toby knows, so I've just got to make sure that he never writes another proposal so that we can do it. So I can prove by hand that bounded resources are necessary to compute any given section of the mesh. What's that mean? That means if I take some element, some cell in, first I have to tell you that in O1, I can compute the numbering of the new mesh. So I know all of the sizes up front because I can consult the table and figure it out. Then I can ask, so I say, the new mesh has 31 cells. What is cell 17? Cell 17 is defined by its boundary. How expensive is it for me to compute the boundary? It turns out that it is output sensitive. So the cost to compute that boundary does not depend on the size of the whole mesh, but it is independent of the size of the whole mesh. What does this allow me to do? It allows me to never make that mesh. So in PETSc, there is what's called an ephemeral mesh, which is the mesh that would have been created with a given transformation, but I don't store it. I just store the original mesh in the transform, and then I compute everything you ask me. So you only ask me questions like, what is the transitive closure? That can be computed in time that's just proportional to the size of the closure. And so you can compose transformations together and still maintain this ephemeral nature. So for instance, one thing I did as an experiment was there's a filtering transform, so I cut out a piece of the mesh, then I refine that piece, then I solve a small PDE on it and project back, and that's homogenization. That's the LOD method. And I never make anywhere the large mesh. I would like to be able to prove that the meshes produced by any given transform are correct. So I think Blaze had a point about that may be geometrically incorrect. And yeah, that would be neat to prove. I would like a proof. I have a by hand of parallel complexity. I'd like to be able to prove that. And proving things like deadlock freedom of the whole algorithm would be great. I know it is, but I have not proved that it is, and that would be wonderful. I can't do everything. So here's an algorithm that I published a long time ago with Ridgway and Peter Brun for coarsening a mesh, and I just can't fit this in to the same framework because you got to know what comes out. And here, there's a lot of online decisions, and it's difficult to figure out what comes out. So I haven't figured out how to do coarsening yet, but working on it. We did figure out, I think, how to do mesh interpolation, creation of faces and edges, but I haven't done it. Thank you. So 0 words. Good.
Any questions? I don't want us to get too delayed from our other speakers, but I just wanted to kind of briefly show what I think of as kind of like a way to formalize this. So your tabulations, in a talk that I gave at Parallel Processing 2020 right before the world shut down, was that your transformations really just represent a polytope of one dimension higher.
Oh, yes.
And so all of these mesh transformations, I think they can be reduced down to 2 fundamental operations, which are attach something to an existing mesh and then delete something in its support. Oh. So like, I've got a single element. My refiner looks like a triangle. It's a polytope of 1 dimension higher.
Okay.
And so my operation is attach, and then delete this and its support, and we get to, this is just here as an extra dimension for visualization, but then you get the refined thing.
Oh, right, because you're saying the things that get reproduced are just identity, and the other things, okay.
And so if you want to, if you want to coarsen, then coarsen is attach this way to get the same thing,
right.
And then you remove those two. So the 2 fundamental operations that you can do for a lot of these transformations are just attach and delete. And I think that it may not make sense to code it that way in terms of ephemerals and things, but in terms of trying to do a proof.
Yeah, oh, that would be neat. Okay.
All right.
We'll think about it.
So let's thank Matt for stepping in this morning.